Welcome to my Atari 7800 basic tutorial. So get your Atari mug and fill it with your favorite beverage. Put on your spectacles if you got 'em, and let's make a thing. Welcome to the Atari 7800 Basic Make-A-Thing Lesson 4. Yes, I'm back. Look at me. That intro was done 2 years ago, and I look 10 years older. So I guess I'll have to do something about that. Here is my new YouTube hat. YouTube hat. I don't even know how it looks. Hold on, let me take a look. Well, that doesn't really fit correctly. Let's get that on. Doesn't really work over with these headphones on, does it? All right, YouTube hat. There you go. I don't know. Let's go with it. YouTube hat. This is my new look, for better or worse. Now I feel like I can continue. Today we delve into collisions and special score variables and a bunch of other stuff. You might notice that these new videos look a little different than the ones from the first 3 lessons. That is because back in 2023, a hard drive crash destroyed most of the support material I used to create these lessons. When I tried to look at the videos, they were all corrupted, so I had to start over from scratch. So now I'm getting back on track. Thanks for your patience. I know it's been a long time. Introduction. First, a bit of an update. In the last lesson, I mentioned that one of my long-suffering unfinished games did not have a title screen. That game is Last Stand Halloween, which was last updated in 2020. Well, after saying that, I went ahead and made a little title screen for it, and I also tweaked the game a bit, and then I made another version in 2024 with the Christmas theme, and they all have title screens now, and you can find them up on itch.io. There'll be a link in the notes. Click on the link below, which will be below in here somewhere. Hey, I'm just talking to you while I'm editing this, and I realize that these lessons are getting more and more complicated. So it would be a really good idea if you click the link below in the description to go to the website that has the text of this lesson and links to the GitHub, because it's probably much easier to follow along that way than trying to replicate all the code that's being shown in the video. Videos are getting more to the point where they can just give you a feel for what to do, but you're not going to get everything from them. You're going to have to go through the code. Sorry about that. It's just that these things are getting more complicated. So let's get started with another sprite, the orb. The orb is the object, the UAP. Hold on a sec. I've got to clean my glasses. Okay, the orb. The orb is the object the UAP needs to collect to open up the next portal to exit the level. You have to collect enough of them to power the wormhole or the portal. I guess it's the portal. I said a wormhole here, but let's say to power the portal and to get out of your quantum layover. Open up the sprite editor and create a new sprite file called orbs.spe. Let's make the orbs 3 colors of blue and look like spheres so they stand out against a black background. Create an 8x8 3+1 color sprite and let's get moving. First, choose 3 colors of different shades of blue so they can handle something that looks a bit 3D. Now, I'm not good at sprite design, so I'll try my best. It takes me some time to figure out what to do when I'm making sprites, and you'll see here that at first I thought I'd make some cool 3D orb in 3 frames of animation. However, my first attempt was not that great. So I started over, changed colors a bit, and it gets a little better, to me anyway. I copied the sprite and edited it to make it look like it's rotating. At some point, I decided to make it 5 frames instead of 3 because I think it looks even better now. But you know what? I think 6 frames might be even better. And maybe we need to make the top and bottom look like they're rotating too. When I'm done, I save the file as orb.spe and I export each file as orb1.png to orb6.png. And now we're going to create the portal. It will be formed by two 32 by 16 sprites to create a 32 by 32 size portal. We'll create 2 frames so it will animate and look kind of like a neon sign. Part 2. Put the orb on the screen. So now let's load in the orb sprites like this. We'll make a similar set of variables like we made for the player to keep track of the X and Y location and the current animation frame and the count we have before the orb animates so that it doesn't animate to the next frame, and every frame it's slower. This should look very familiar. Now let's initialize these variables so the orb will display at 50/50 on the screen. The animation frame is 0 and the animation weight is 0. Next, we will set a color palette for the orb based on the colors we use. We'll use color palette 2. Remember, color palettes start at 0, so this is actually palette 3, but it's 2, P2. Now here's the code to animate the orb on the screen. We plot the sprite just like we plotted the player sprite, and we do the animation frame and the weight just like we did with the player. So now we're ready to test it. Compile the code and launch it. Press the Z button to get to the title screen, and you should see an orb rotating at 50 by 50. But something is wrong. It looks like the colors are swapped in the palette. Let's move those around a bit like this. Notice that we've instead of going 0, 1, 2, 3 for the colors, we did 0, 3, 2, 1. Now test it again. All right, the colors look good now. There we go. If that had not been right, we would have kept trying until we got the colors correct. Part 3. Just how many objects can we get on the screen? If you use the link to download the Atari 7800 basic package from GitHub, you'll find a number of sample programs in the /samples folder. One of them is called 101, which I believe was written by RevIng Mike Sarna. You'll find it in the examples folder. Go ahead and load the file and examine the code. I quickly changed the extension from .baz to .78b so it loads correctly in Visual Studio and acts like a 7800 basic program. This is a fun program to examine and execute because it shows over 100 objects moving on the Atari 7800 screen with little slowdown or corruption. It's fascinating to see. It gives us some ideas on how many objects we'll get on the screen for UAP. Part 4. Randomly place the orb. We don't really want the orb to be at 50/50 on the screen. We want it to be randomly placed. Here's the code to do that. Rand will create a random number between 0 and 255. Of course, the Atari 7800 Mode A screen is less than 255 by 250, so we must limit the random value so it's placed on the visible screen. The width, we'll limit it to x being 151. For the height, we'll limit it to the orb being less than 183. We also need to actually draw the orb on the screen, which looks a lot like how we drew the player. Notice that we use 2 for the palette in the plot sprite command to match the palette we defined for the orb. Now test this. And test it again, and test it again. See that the orb is placed randomly, but since the random number sequence is the same every time, it's placed in the same place every time. This is not an accident. Think of a game like River Raid or Pitfall. The only way games like those, with seemingly so many levels and an endless river, could be shoved into Atari 2600 cartridge was to make use of some kind of repeated number sequence. I once asked David Crane this question. He told me that he used a polynomial sequence. He started with the random numbers, but found a sequence that worked, and then built the game off that sequence. If the sequence was always random, the game would be totally unpredictable. The random number generator for the Atari 7800 uses a predictable sequence of numbers. However, for our game, we'd like an unpredictable random number. To do this, we'll use a seed value that starts the random number generator at an unpredictable place. First, we'll define the seed. Then we'll put some code in our title screen that updates the random number in each frame, then sets it back to 1 if it's greater than 254. This will make sure that we have some random value to place into the rand variable. you see the random value like this. You say rand equals random seed. And then we get the orb x and orb y as random numbers, and we make sure that they are within our acceptable values. Now test this version. And test it again. See, by using random seed, we can achieve our desired result of having the orb placed somewhat randomly on the screen each time the program is executed. Part 5. Pick up the orb. So, good, we have two independent objects on the screen, but that's still not a game. To make this a game, we need those objects to interact. First, let's... Hold on a sec. I had to get the dog. Sorry about that. Let's see how this hat goes on this time. I don't know if this internet hat is going to work. Let's find out. Just a sec. I got to look at myself because this is going to look bad. Oh, that's all right. Let's keep it like that, I guess. All right. All right, internet hat. There you go. First, let's update the score. We made a score variable, but we never used it, and we don't need it, so we'll comment it out. The basic predefined variables in 700 Basic can only hold values between 0 and 255, but scores are usually much more than that. Instead, we'll use score 0, which is a special variable defined by Atari 700 Basic that can hold a 24-bit value. Initialize it like this: score 0 equals 0. Score 0 variable is a BCD, a binary coded decimal, which means it can't easily be used in operations with other 7800 variables, but we can add numbers to it, which we will do when we test a collision and see if there's a score. We will print the score on the screen using a plot value function. The plot value command lets you plot numeric values as text. Hey, this is Steve. As we're editing this, I wanted to say I realized I forgot to remind you of the plot values on the screen directive that we set a long time ago in an earlier lesson. That directive allows us numeric values on the screen. So just so you know, we had to have that set so this will work. One thing that is tricky about plot value is the fourth parameter, which in this example is 6. That is the number of characters to print on the screen. In general, score 0 is a 24-bit number, so I always print all 6 characters. Now we create a new subroutine named random orb and use that function to create a new orb every time we need it. We'll call it with go sub random orb. The subroutine looks like this. Orb x equals rand, orb y equals rand. Remember, we already seeded the random number value. If orb x is greater than 151, then orb x equals 151. If orb y is greater than 183, orb y equals 183. This is pretty much the exact same code we had before, but now it's in the subroutine that can be called as many times as we want. Okay, now we're ready to test if the objects collide. The simplest and easiest way to do this in 700 Basic is to use the box collision. This function lets you see if a bounding box of one object is overlapping with another, and if so, it returns a positive value. Of course, box collisions are not always the best way to efficiently perform collision detection, but it will work fine for our game. Box collision has 8 parameters: the x and y location of the player, the width and height of the player, the x and y location of the orb, and the width and height of the orb. We will also make another subroutine named test collisions and call it like this: go sub test collisions. This call will come right before we plot the score on the screen in the game loop routine. In our code, if we test a collision between the orb and the UAP, we'll simply create a new random values for orb and xy and keep going. In this subroutine, we use box collision to test a collision between the player and the orb. If we detect it, we'll add 10 to the score and call random orb again. If not, we will use a goto shock to skip the code. Now let's test this version and see what we have. You can collect the random orbs all day long and rack up your score. Okay, this is the biggie. Part 6. So now I know what you're saying to yourself. Sure, one collectible seems simple, but what about having 32 collectibles all zipping around the screen at the same time? your number might not have been 32 in your head, but I making it 32. Well, honestly, we do it in a very, very similar way. First, we'll comment out the code that defines the variables for a single orb. Instead, we'll create a set of variables to hold temp values that we'll use in our code. We need these because operating on arrays in Atari 700 Basic doesn't always work for every function, and we need to take values out of arrays and put them in temp variables. You'll see this in a sec. We will also create a few new variables. First, the x and y velocity variable to hold the current speed of the orbs so we can move them around the screen. We'll also create a max orbs variable that will limit the number of orbs on the screen on a level. Now comes the interesting part, to me anyway. We need to define the space that holds the data for the orbs. We want to have a lot of orbs to collect. Let's say we want 32 orbs. Each one is a separate x location, y location, x and y velocity, animation variables, and a variable to track whether it's been collected or not. If we use 1 byte for each of these values, that would be 256 variables. But we only have 126 predefined single byte variables in Atari 7800 Basic, so how on earth will we track up to 32 orbs like this? Well, besides 126 predefined variables, the Atari 7800 also has about 1.5K of usable memory for a game. We can make use of that memory to store the values for the orbs. The memory starts at location 2200 and ends at location 27FF. You can also access an additional 16K of memory if available. Remember, we use that to expand our display list in one of the earlier lessons. Now, we'll start by writing dim orbx equals $2200. This defines the variable orbx to the memory location 2200 instead of to a distinct variable. We then count 32 bytes in hex, not decimal. This defines the next variable, dim orb y 2220, and so on with orb x velocity, orb y velocity, orb anim frame, orb anim weight, and orb captured, each time counting 32 in hex from the last variable for the new one. It looks like this. Now we have effectively defined the space to hold the orb data. Now what stops you from defining the variables wrong, counting the hex wrong, or defining other variables on top of these? Nothing. You need to keep track of all that yourself, so be careful. Now we'll initialize the temp variables to 0. Next, in the init game function, we set the max orbs to 32, so now we can draw 32 orbs on the screen. Then we will create the orbs to display by calling a make orbs subroutine that does not exist yet. So let's make the make orbs subroutine. This is the heart of the solution of tracking up to 32 orbs at once. First, we create a for next loop that counts up the number of orbs and max orbs, -1 because we start at 0. Then we use ran to get random numbers between 0 and 255. We use these values so that some of the orbs start off the visible screen. We place those random numbers in orb xi and orb yi. The bracket I bracket after the variable is array notation for the index of the array. We use it to access all those spaces in memory we skipped when we defined the variables. That means that each one of those variables will hold data for all the orbs accessed by the bracket I bracket index notation. That makes orb x and orb y and all the other variables parallel arrays. Since we can't easily define structs or objects in memory in 7800 Basic, we can instead use parallel arrays, which will make working with large sets of similar on-screen objects much easier. Now, we set some random velocities for the orbs so that they will start by moving in different directions on the screen. The values between -1 and 1 are the number of pixels the orbs will move in the x and y direction each frame. This means orbs will move in 8 different directions. We also set orb anim frame, orb anim weight, and orb captured to 0. Now we'll update the game loop subroutine. Instead of moving and displaying the single orb on the screen, we'll run through a similar for next loop to the one in make orbs, making use of the temp variables to store the value from the parallel arrays as we iterate through them. We need the temp variables because, again, 7800 Basic doesn't do well trying to use the values in the arrays directly using the index notation. We also use m as the iterator set to max orbs -1 because, again, the index of the orbs starts at 0. We also need to delete the random orb subroutine, then comment out the code in test collisions that calls for a random orb. We should now be ready to test the code, and here is what it looks like running. Now you can see all the orbs zipping around the screen. This is what it looks like running. Part 7. Collect the 32 orbs. Next, we'll let the player capture the orbs. To do this, we'll create two new variables, temp captured and player speed. In the init game subroutine, we'll set the player speed to 2. This way, we have the option to increase or decrease the speed later instead of it always being a constant. We'll then use it right away in the game loop subroutine by removing the discrete values we had before and using this variable to update the location of the player when the joystick is pressed. We'll also call a new subroutine named test collisions so we can have the UAP collect the orbs. Now we will build the test collision subroutine. We will iterate through the array of orbs very much like we displayed them on the screen. We will test orb capture to see if the current orb is already collected. If so, we skip the rest of the code, jumping to skip collide. Next, we are ready for the collision check. We have to be careful because this code checks box collision up to 32 times per frame, depending on how many orbs are left to collect. This will work fine, but if we keep adding more and more checks of this side to the test collisions, we may need to optimize further to make sure the call can run inside a single frame. Back in lesson 2, remember 2 years ago, we talked about the double buffer flip 2 command in Atari 700 Basic that we are using to draw the screen. This gives us an effective frame rate of 30 FPS, but also allows extra time to complete these types of checks. If we do find a collision, we update the score 0 variable with 10 points and set the orb captured for that orb in the array to 1, which means it's true. Now let's test this and capture some orbs. Go, 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 collect them all, collect them all, collect them all, get all those orbs. It's kind of hard to collect all the orbs the way the code is written now, but you can do it, and it's starting to look like a game. Part 8, but why is it so hard to collect them all? So you may notice that not all of the orbs display on the screen at the beginning, and some may actually be assigned movements to make them nearly, if not ever, appear on the screen. To help with this, we'll make sure the orbs always start on the visible screen. We do this by making sure temp X is always between 0 and 152, and temp Y is always between 0 and 184. When we get the random numbers for each, we'll loop back to new labels getX and getY until we find a number within the range, all in the make orbs function. So let's test this one. Try it a couple times. Okay, let's test this one. Now let's test it again. You'll see that more orbs appear on the visible screen now before they fly off into the ether. Part 9. Display the portal. So now we will end the level and display the interdimensional portal so the UAP can travel beyond the current ranch to the next ranch, wherever that might be, when the level is complete. Here's the portal we designed way back at the beginning. Now we'll load the sprites in like this. Hi, this is Steve on my 7th day of editing this, and I just noticed that I forgot to mention that we create a new variable named level here to hold the current game level, which is important for this lesson, so sorry about that. Now we will define a similar set of variables for the portal that we defined for the single orb. Those variables now deleted, the X and Y animation frame and the animation weight. We will also define a new variable named orbs left that will help us keep track when the level is completed. So now we define the level as 0 and we set the colors for the portal as we defined in the sprite creator. Next, we'll remove the call to go sub make orbs from init game and move it to a new subroutine named init level. This is because we want to remake the orbs before every level, so there's no need to do it in init game. We'll do it in init level. We increase the level in init level because it is set to 0 when we start. So now we can call this subroutine every time we want to start a level. Then we set orbs left to 32 and the X and Y position for where the portal will be displayed. Now we will add the code to display the portal when all the orbs have been collected. We will test the orbs left variable to see if we should display the portal. If the number is 0, we'll call a new subroutine named display portal. We will also test to see if the player has collided with the portal. If so, we will call the new init level function to start a new level. We do not want to change levels if the player touches just any part of the portal. Instead, we add 10 pixels to the X and Y location and only test a 6x6 region inside. We want this so that the player needs to actually enter the portal to go to the next level. Also in the game loop, we'll add some new code to where we display the score. We'll add some text for orbs left. To do this, we'll use the convert to BCD function that converts a hex byte variable into a decimal number, 0 to 99, which is good for displaying stuff like percentages and orbs left as long as it's less than 99. In this case, it will be used to display the orbs left. We put the converted value into the K variable to display it on the screen using plot value. Next, we will add some code to the test collisions subroutine. We'll add one line of code here to update the number of orbs left if the player collects one. Orbs left equals orbs left minus 1. Finally, we create a brand new subroutine called Display Portal. This is very similar to other places where we've displayed sprites. The difference is there were 2 portal sprites to display. Wow, that's a lot. Let's test this version and see what happens. We should see the portal appear and the player should be able to enter it and move to the next level. Part 10, cleaning up. Okay, we have some cleanup at the end of this lesson. I noticed that some of the label names were confusing. We need to rename the subroutines to be different from go-to labels. Let's make sure all the go-to labels have an underscore at the beginning and all the subroutines do not. Like underscore set title colors is set to set title colors. Like underscore title loop is set to just plain title loop. But we also need to make sure that the call to title loop is updated at the end of the subroutine. Also change the underscore init game to just init game. In the title loop, then we need to call init game instead of underscore init game. Underscore init level should be called just init level. But then we need to update the line of code in underscore game loop, which will soon be just game loop, to call init level. Also, in init level, change the call to underscore make orbs to just make orbs. Underscore game loop is changed to game loop. On the last line of game loop, change the line of code to call the correct subroutine instead of underscore game loop to just game loop. Change underscore test collisions to test collisions, then change this line in the game loop to go sub test collisions instead of underscore test collisions. Change underscore display portal to display portal, then change this line of code in game loop that calls display portal to instead of underscore display portal to display portal. This is a good chance to practice your skills debugging 7800 Basic, as you will probably not get all of these right the first time. Truthfully, it might be easier for you to just pull the lesson 4 underscore 10.78b file from the Github repo and start there. Now let's add a couple more things to finish up. First, let's add random values to the orb anim frame from 0 to 5 so that the orbs will display with a different start frame and not look all uniform on the screen. The last lines in the for next loop in the make orb subroutine should now look like this. We get a random value, and then we set the orb frame depending on what that random value is. Notice that orb anim frame has now been removed, that we once set it to 0, now we're setting it to one of the random values. Finally, let's limit the player's UAP so it stays on the visible screen. Add the following lines of code right under the place that you test the joystick in game loop, not underscore game loop. Remember, now it's just plain game loop. These values will keep the UAP on the visible screen and not let it leave. Now test it. Your player stays on the visible screen. You can collect all the orbs, and if you collect them all, hit the portal, and you can leave for the next level. You know, I think after a 2-year break, you deserve a bit more meat for this lesson than the last one was just about title screens. Next time, we will turn this UAP sighting into a full-on battle in the sky. And there you go. Lesson 4, Atari 7800 Make a Thing, coming up, Lesson 5. Thank you for sticking around with me. I'm sorry there's a 2-year break. I hope you like the new internet hat. And let's just keep going on this and finally make a thing. For Into the Vertical Blank, this is Steve. Out.